Hello, everybody, and welcome to this month's Northwest Quantum Nexus seminar series. Before we begin with introductions, we have a couple of announcements we'd like to make. The first is a disclaimer. The seminar is being recorded. So by attending the meeting, you may appear as an attendee in the recording. Your questions and comments will also be part of the recording. And so if you have any problems with this, we encourage you to log off now. The NQN seminar series is governed by a code of conduct. The Northwest Quantum Nexus is dedicated to providing a respectful, friendly, and professional experience for everyone, regardless of gender, sexual orientation, physical appearance, age, race, or religion. We do not tolerate any behavior that's harassing or degrading to any individual in any form. Individuals are responsible for knowing and abiding by these standards, and we encourage everyone to assist in creating a welcoming and safe environment. The Northwest Quantum Nexus reserves the right to refuse admittance or remove a person from any person from the event at any time at its discretion. So with that, I'd like to welcome Aspuru-Guzik, who's professor of chemistry and computer science at University of Toronto. He began his independent career at Harvard and in 2006 and was a full professor at Harvard from 2013 to 2018. He received his Bachelor of Science from the National Autonomous University of Mexico and a PhD from UC Berkeley in 2004. Alan is known for many different things. He has done exceptional work in quantum information processing, and you could probably fill up a talk with that alone, but he has very exciting and diverse interests, including his work on materials and some very exciting research in automation, particularly the notion of autonomous chemical laboratories and the acceleration of scientific discovery through autonomy. So today we'll be hearing about, I think, a small fraction of his diverse research portfolio. He's received numerous awards for his work, including the Google Focused Award for Quantum Computing, Sloan Research Fellowship, Camille and Henry Dreyfus Teacher Scholar Award. And I think if I read them all, we'd probably chew into too much of his presentation time. So with that, I hope you will join me in welcoming Alan, and we look forward to hearing his talk. Alan, over to you.
Thank you, Nathan. This is a pleasure to be here in the Northwest virtually, and hopefully one day I'll be in person there. I'm gonna start sharing my screen in a second. Okay, I imagine now you guys can see my deck. So I'm gonna get started. I cannot see your questions, so I'm gonna reserve questions at the end. I was asked to speak for about 40 minutes. I'll try to get it to 40 or less, and then go into Q&A. So please start typing your questions, and then I'll get to them at the end. I apologize. This is just the Microsoft Teams kind of interface. Okay, so let's just hop into it, right? I'd really like to start this type of more general talks about quantum, reminding you how important is simulation. This is an example of the Antikythera, a machine that was built by the Greeks 2,200 years ago to simulate the motion of the planets. Okay. And it's kind of cool, it even predicted the next Olympia. This is basically a gear mechanism. It is classical mechanics simulating classical dynamics, right? I mean, as it was perceived, of course, from the vantage point of Earth and so on. So, I mean, that sophisticated gear mechanism, right, tells you an idea of how important humans have been thinking about simulation. More modern, it is this beautiful history of physics book by Peter Gallison, which is a professor of history at Harvard, who writes about the birth of computer simulation. And I mean, a place like PNNL, DOE, right? Of course, Microsoft as well, and UDOT, right? Computers are used all the time for designing things, right? And what is really cool about this quote is that it tells you that the world as we know it will not exist without the virtual counterparts of simulation. So in this talk, I'll come back to those virtual counterparts and think about how can we do with quantum computers to generate these virtual counterparts, right? For example, just the chip that I'm using to give you this talk was designed by a chip, right? So the world is very meta right now in terms of simulation. Now, let's think about simulation for molecules and materials. This is Samuel F. Boyce, the advisor of the advisor of the advisor of my advisor, okay? Something like that, okay? 1955, used this computer called the EDSAC to simulate the electronic structure of molecules in a general way for the first time. Okay, and his student who got the Nobel Prize, John Popple of Nick Handy and Asa Shavit, talked about his presentation of the first computer program that simulated a molecule in 1955 in the Boulder, Colorado. So in 1958 in the Boulder, Colorado conference. And you know, he talks about a question coming in one side, an answer coming into the other. And I really like that thinking or that idea because now in the modern world, it means AI to answer questions like with, you know, natural language models. It might mean many things nowadays. It's still an open question. So you can always historically back and read this quote. What he meant really though is the structure of a molecule giving you its energy or a measurable molecular property. Another one of the pioneers of this work actually is Richard Feynman. There was just a conference at IBM about the 40 years of this paper, right? This paper is very important because it's Feynman's most cited paper. Talks about not only the idea of quantum simulation, but also the idea of quantum computing. So if you have not read that paper, check it out. It actually is very prescient. And I'm very sad that I guess in some sense the competitor of Microsoft, Apple, has gone downhill in quality of ads over the years. Look at the current ads. They look so much crappier than that beautiful Feynman ad. So this is a call for action for better Apple ads. So what is the way of the simulation, right? Kind of like the way of the Mandalorian, right? So what we do in quantum simulation is take a quantum system, create a quantum model, time-independent or time-dependent Schrodinger equation. It could be either of them, or relativistic models, or it could be all sorts of other models as I will be discussing. But then if this is a quantum model, then it's very natural to map it to a quantum information processor. And this mapping is efficient. That's where Seth Lloyd came in. Very important papers of Seth Lloyd in the 90s that show that this is the case, that local Hamiltonians can be simulated efficiently. And if you simulate a Hamiltonian efficient, and by simulation here, I'm meaning time evolution. Preparing the ground state is a different question. And then finally, you can taking that state, you can actually, you know, project out or measure classical values, right? So you cannot read the entire full wave function. That's not efficient. But having said so, it's usually not necessary for any observable that you really care about. So this paper was written again now by the student of John Pop, sorry, of Samuel Boyce, my postdoctoral advisor Martin Head Gordon, and I was in his group when I did the first paper in quantum computing for chemistry with him. But in this paper that he wrote back in 2008, you know, almost 15 years ago, he was predicting what is going to be the growth of the different classical methods for simulating the Schrodinger equation on classical computers. Talking at an audience at PNNL, many of you might be familiar with the use of this, for example, the prediction of environmental properties and all the things that people do at PNNL. And you also know the limitations of these methods. Back then, I put this plot in a museum in Japan, actually. What if you had a polynomial scaling method, such as the quantum computing simulation methods? Eventually, we'll be crossing the exact simulation, and it will be better off to simulate that system exactly with a quantum computer rather than approximately. And then you will move on to the other methods, effectively retiring them. Obviously, this curve has not grown as fast, but we'll talk about how fast these things are growing. You know, different to quantum supremacy, we like to call quantum advantage, is when a quantum computer outperforms a classical computer at any practical task. Now, I'm going to say something. First thing I'm going to do is taking advantage of PowerPoint. I'm going to just fix my slide. But anyway, one of the things, can you guys see my slides? It says sharing is possible until you return to the shared window. Did you guys see my slide?
We see one that says disruption in quantum simulation.
Yeah,
it has a blue box and a black box.
Perfect. Okay, I just was fixing it and then I realized maybe I messed up. Okay, so I co-founded a company called Zappata Computing. It's growing very rapidly. It is a quantum computing software only effort, right? We work with a lot of partners. The definition of Zappata of quantum advantage is the one I really like, which is by any means, it doesn't matter if what happens in the quantum computer has a provable speed up of any kind or something more formal. If for any reason whatsoever, a commercial entity decides to replace a process that they have by a quantum computer as an auxiliary processor, almost like a QPU for some reason. It could be heuristic reason, it could be it could be a reason of convenience, etc. Then I believe that's the moment where quantum computers become commercially interesting. And Zappata computing is aiming to achieve that. And that's one of the things that I think many of the people are thinking about. And from that perspective, these discussions about if the Bigue quantum computer is quantum or not wouldn't really matter that much, in the sense that if that machine is employed for a practical task, really in production in somewhere, then we will have achieved quantum advantage in our opinion. And it could be, of course, a gate model machine or any type of machine. We mostly, if not surely, we'll be talking only about gate model here. This audience is although diverse, also it's a quantum seminar, so I'm gonna skip the introduction to quantum computers. Needless to say, I'm just using the traditional gate model of quantum computers that I just remind you about in this slide. I'm gonna also skip my description of quantum algorithms and my description of quantum gates. But maybe what we wanna think about here that is important is, of course, what makes a quantum algorithm in the near term important. It will be how many gates can you do before enough errors creep in that your system is not really usable. How many qubits do you have? And usually right now, the depth is actually, or of course, related to the rate of the coherence, is actually more problematic than the number of qubits. People can build machines with more qubits than we can effectively employ given the error rates that they have. Okay, so I would say if you are a hardware person, you really should think about, of course, improving coherence properties, but also improving control properties, improving materials, as you guys all know. So we are working again in the concept of just universal gate set, so traditional gate model quantum computing. And now, keeping up with the history, right? I'll mention work about Martin Head Gordon. So when I was his postdoc with Tony Dutoy and Peter Loeb, which at the time was in Vancouver, I guess in the Northwest.
Sorry, excuse me. Yeah. We are not seeing the slides. We're still on the disruption and quantum simulation slide.
Are you serious? Oh my God, that's problematic. I don't know why. Let me unshare and share again, if you don't mind.
Yep, that will work.
There you go. Give me 1 second, okay? That was pretty sad. Well, happy that you interrupted me. Can you guys see my slide now? Can you guys see quantum computers intro?
Yep, we can see that now.
So I don't think there was anything crucial about my slides. So you heard me. So I imagine everything I told you without slides, and let's continue. Okay. So this is where quantum computing for chemistry, I guess, started as a kind of field, so to speak. Here we're using the so-called phase estimation algorithm, which is, for those of you that know some physics, is very cool because it really is nothing more than the Fourier transform of quantum dynamics, a little bit like the Fourier transform of the autocorrelation function that you do when you do quantum dynamics. You time evolve a quantum system in successive powers of 2 of the unitary time evolution operator, which in turn rotates at this. The eigenstates of such an operator will rotate at a speed proportional to their energy. Therefore, with this very simple formula, you can read out the energy out of that phase. So this is nothing more than a time domain algorithm that at the end of the day is Fourier transformed. And then, depending on one of these energy peaks that you read here on the left, you will actually collapse the wave function to the ground state of that particular, to the state associated with that particular state. Therefore, if you have a state that has a good overlap with the ground state, then you will be able to, statistically be able to read the ground state or low excited states. Okay. My group and I have worked on several things, including many other people in phase estimation. What is still relevant, actually hasn't changed very much since the last 15 years, is the mappings. Doesn't matter which one of these lines you look at it here, the details are not so important. What matters is that these are enough orbitals, enough angular momentum functions mounted on each one of the atoms to reach what is called, to reach something that is accurate for the chemical standards, at least as of 15 years ago. Definitely you could do better now. But the point given is that molecules of the size of cholesterol will require of the order of thousands of logical qubits. So, of course, many of you probably are aware in this symposium that we're in the noisy intermediate scale quantum computing era, this era where, we are trying to move from this classical world. We have these computers that I was describing a little bit before, computers that can only execute a certain number of gates before they decohere. A lot of work, including my groups and others, has been done on error mitigation, which allows you to actually extend use a little bit. And then the question is, will you be able to have some application before we reach quantum tolerance? I like to say that if the first time people actually build a quantum computer with a perfect quantum memory, I predict that's going to be an overprice for sure, because we really are creating a new phase of matter, right? Some sort of quantum system that has no decoherence due to our operations, right? And it could last years. So I think the first time somebody can have a qubit last forever, or at least for order of years, that would be extremely exciting. But we are not there yet, and it will take perhaps a decade. I don't know exactly how long. So let's just think about what we can do now. So now I'd like to show you this picture of 3 reviews that was involved. One in 2019, one in 2020, one in 2021. You might say, oh, Alan, you're getting old. You're almost 45. That means everybody's asking you to write reviews. This is not the reason. This is a review that came out of an NSF workshop that we did on the topic. This is mostly my group members and I. And we actually, all my group members and I at the time, and now co-founders of Zappata Computing, many of them. At the same time, there was this other review in Red Mod Phys with Sam McCardle and Simon Benjamin, Suguru Endo, and Xiao Yuan. More of a physics perspective on the same problem. But then you might wonder, why did I decide with my group, which is mostly my quantum subgroup right now here, why did we write this one that we submitted to Red Mod Phys? Well, because we couldn't catch up. And we decided that a good exercise would be to work together and see if we can see what's happening in the NISQ algorithms. So the NISQ algorithm started around 2012, 2013. I'm very proud of being part of my group actually proposed the so-called variational quantum eigensolver. This is Gerald McLean and Man-Hung Jung in my lab in collaboration with the group of Jeremy O'Brien, Alberto Peruzzo, now in Australia. Proposed the idea that maybe the best thing to do is to concentrate on measuring the expectation value of the Hamiltonian and preparing quantum states that we variationally optimize. You have to contrast this to phase estimation, because in phase estimation, if you have sufficient overlap with the ground state, you can read the exact energy. Whereas here, you are kind of bound by the variational principle to not be completely exact. You can see it actually, as a matter of fact, in this dissociation curve in this plot of a paper that I will show you later with Google. You can see how the exact simulation doesn't match the VQE energy, because the VQE is an ansatz. And even though it looks noisy, this was a quantum computer carrying out a phase estimation algorithm that in principle will be exactly on top of that black here. So at the same time, Eddie Farhi proposed the QAOA algorithm, which is kind of like the cousin of the VQE. And then since then, we started working on the so-called quantum autoencoders and variational generators and other type of applications that have to do with quantum machine learning. This is work from my lab. But in all of these, we minimize or maximize something. So that's the reason why there's a deep connection between quantum machine learning and quantum chemistry and quantum optimization and so on. In all of them, we have an objective function that we optimize in the quantum computer. So now this is the table of NISQ algorithms that we put together in the paper. We are going to make sure that this is updated. We'll put a website up that it will be a live database, so people can keep helping us add the new papers. But notice why we said we need to write that paper. Most of the papers that you see here are in 2019 and 2020, right? So these are all algorithms related to the VQE, let's call it this way, algorithms related to many body simulation. And I'm going to read them for you. You can see my screen online, but you can see there's tons of them. Then another area that is very important is quantum machine learning. Today, I'm gonna just mention it in passing, although again, we were pioneers of the quantum autoencoders that happen to be here because they have applications in quantum simulation, but also on the quantum adversarial networks as well, together with all these other people here. But there's all sorts of different work here, and it's very, 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 very rapidly advancing. Combinatorial optimization is also getting a lot of attention. For places like PNNL, of course, DOE type of interests. The whole movement of trying to do linear algebra, subroutines on quantum computers, I think will be quite important. Nonlinear PDEs will be quite important for DOE applications. And finally, an area that I think is going to become more and more exciting will be finance, because obviously, ultimately, people want to make money. And then there are all the other applications for NISQ, including our own quantum variational error corrector that allows you to use a NISQ type approach to error correction. But obviously, there's all sorts of different applications. The ones for metrology seem to be quite cool and interesting. Okay, so what is under the hood? Okay, so the way I like to think about it is think about it as tuning a guitar. The tuning has to do with the gate parameters that are usually in a stencil. Obviously, nowadays, people also build the circuits on the fly and variationally optimize the circuits as they compose them in several schemes. But what I mean by that is they compose and measure, they change the circuit discretely and also continuously, parameters and also gate or not gate. That's what I mean. Usually in a constructive manner, adding more and more gates and seeing what happens. But ultimately, the observable is a game that you can play. Ultimately, all of the encoding happens here. How do you put the energy function for this particular thing? And as you know, in machine learning, there's many loss functions that you can add. You minimize such a function and then update the parameters outside. All of it happens in a classical computer and then come back. A lot of the work has been done recently on gradients. We'll come back to it. So because we started the BQE work, and also because obviously it's dear to my heart in terms of quantum simulation, I would like to continue talking about the BQE. A very important thing that we say in the BQE paper, and I think is very important, we introduced, as far as we know, the word QPU there. Maybe others did before, but I think we put it first. And what is super cool about this idea of the QPU is, well, in the BQE, because you can measure the expectation values of the Hamiltonian independently, you could have a room full of quantum computers, right? So I find it quite funny when people are saying, oh, but this will take on a quantum computer, this will take 6 weeks. Well, you know what? Then you just buy more, okay, and put a room full of them. So I keep saying this in my talks because these timings of 62 days or 30 days or whatever really don't mean too much, because then even single cores now are very parallel, right, in classical computers. So what exactly do you mean by a quantum processor will change in time, and it will involve, I think, very, very soon, the concept of parallelism, say a room full of quantum computers with 100 qubits each, logical qubits, say, or even physical qubits, okay? So that's going to happen, and therefore, when you think about these timings, just pay attention. So what happens on the BQE? This is not a super technical talk, but what you do is you have to build these generators of the different terms of the Hamiltonian, convert them into circuits, okay? And for that, you need to map all the Fermi operators of these generators that are in second quantized form into distinguishable spin-on-half particles, aka qubits, and do variational optimization. And if I was giving you this talk 5-6 years ago, I would be going through all this process. But now, I think it's fair to say that there's so many software, there's so many things going on in this space that this is kind of routine. So what's happening in the fast-moving BQE landscape? I think this slide I prepared like half a year ago, and it's already obsolete in some sense. So many things are going on. People are optimizing the ATSAT. Huge work, as mentioned in the next slide, about how to reduce measurements, excited states. Very, very cool work in optimization to try to avoid the so-called barren plateaus, etc. For example, just the work between some of my former students involved in Google, the work of our collaborator at University of Toronto, Artur Ismailov. By the way, I know we kind of quote-unquote stole from you, Nathan Wiebe. We're very proud of that. Nathan is now with us. Hopefully we didn't steal him, but rather he moved back to Canada. And so Nathan is also now joining U of T, and this beautiful group meetings with Arthur and Nathan are legendary now. The three groups together. But Arthur worked he knows a lot about the algebra of these operators and has reduced the cost of doing the operation by grouping smartly the different qubits and figuring out what measurements can you do after you did some measurements. Complicated work. I don't follow all the details of everything that has been happening in this field. Needless to say, what I care about is the scaling of it, because it means that less and less measurements are needed as all these different measurement schemes are being implemented. And something very beautiful about these variational algorithms is that most of the developments can be combined with each other. So every time I tell you something about measurement, it can be combined with a new way of getting gradients, or with a new way of doing optimization, or also with a new ansatz. So you have to think about all of this as synergistic. And for that reason, we developed a package that I am advertising here because I would love people to look at it. My first 2015 quantum computing paper on quantum computing for chemistry was called Tequila. So I think it was fitting to call Tequila again our new package that basically stands on the shoulders of giants and uses Psi4 Pi SEF, JAX, Open Fermion, etc. And of course, all these backends, including Microsoft's, Google's, etc. To actually run. Actually, no, sorry, I don't think we use Microsoft. Sorry, that didn't mean to be bad. I confused it. This queue is not the Microsoft. It's actually another simulator. This is the Rigetti. Sorry, but basically, it won't be hard to actually run it in Microsoft if we want it. But the point is, like, we basically run our circuits and execute them by standing on packages such as Open Fermion, automatically differentiable packages that allows us to actually write VQE type programs and quantum machine learning programs in about 10 lines of code. Okay, and very high level, fully differentiable. And what's really cool about it is that then the algorithm development in my lab and others that use Tequila has exploded. This is a very similar package to another package called Penny Lane, but it has the advantage in some sense that we built it for chemistry. And we believe the interface is very, very, very high level. So this is an example of how to pick the right orbital symmetries and orbitals to simulate the benzene molecule. Just for those experts in the audience. So what is going on? So some examples from my own work. What is going on besides what I told you from other groups? One of the most important things that's happening is people are really thinking about what can you do in the classical side of things. Okay, in other words, in the classical computer side of things to get, for example, better mapping. So the traditional way of doing a mapping, you will just run a mean field calculation and get a basis in a fixed basis set. But if you actually use actually a very heavily DOE supported tool called Madness, which is a multi-resolution grid tool, you can actually have extremely tailored basis set. Okay, basically related to your problem, like basically grid-based orbitals that you can correlate to get natural orbitals from it, per natural orbitals, which are extremely superior to the traditional molecular orbitals, where we would start already the BQE. So notice that all of this work can be done just to map better, and then run it with all the tools I told you before, like new optimizers, new ansatz set, etc. And what this allows you to do is to gain tons of accuracy for free, because the closer this black curve, which is this gray point, which is extremely close to this black curve, which this gray point will be the complete basis set extrapolation. You can see this black curve is very, very close. It's a huge basis set for this particular hydrogen molecule. You see how we can get the hydrogen molecule basically with only 4 qubits if we use the right this basis, okay? Which basically shows you that roughly you can see the factors here, our estimates of the extrapolation to the complete basis set limit. You get factors of 2 to 10 or so in the number of logical qubits by doing nothing other than running a better classical calculation. So this idea that classical supercomputers will be useful for quantum computing is already being shown here. You could imagine that if you have a quantum computer with a large enough number of logical qubits, you definitely want to do something like MRA VQE. Of course, you can use other technologies, for example, entanglement by DMRG and tensor networks measure the mutual information between different orbitals and adaptively build the best circuit. As I was telling you before, this is a new fashion that is happening in the last couple of years, very similar to AdaptVQE by Mayhall and others. So a very beautiful kind of way of actually also improving your answer set. This paper, I haven't updated my slides, but it's already impressed in PRX Quantum. And we really like it because what this paper is telling you is a combination, and it's called the meta-variational eigensolver. What the MetaBQE does is, again, all the games here are, and I've been trying to show you games about everything. I show you games about measurements. Now, then I show you games about the classical preprocessing that you can do and mapping into orbitals. Now I'm showing you a game where you change the objective function. We're going to imagine that we have a Hamiltonian that depends on one or a few parameters. For example, the distance of a molecule, or two rotations. For example, a potential energy surface. Or if it's a many-body Hamiltonian, maybe it is the strength of the coupling over the site energy, etc. So this is a typical parameterized Hamiltonian. So what we do is we measure the Hamiltonian expectation values as a function of a selected number of points along that variable, say 10. Okay, so not all of them because we want to be able to interpolate, but you measure say over 10. Okay, then you're going to then do ansatz say over those 10. Okay, but we're going to add a quantum machine learning layer that is trying to learn how to change your wave function as a function of that parameter. Okay, so in some sense we have this new variational freedom that allows us to have a wave function that depends now on all the parameters of the circuit, but also this external parameter lambda, and we optimize all of that together. That optimized nonlinear encoding meta-variational quantum eigensolver, for example, as we call it, will give you very, very, very little error. For example, for this famous stretched H4 problem, these 4 atoms here, compared to the traditional variational eigensolver. In some sense, it's able to actually see what happens at the two sides of this kind of like, critical point in the wave function where you're changing nature in the wave function, but also interpolate between all the different points in the potential energy surface. So MetaBQE, again, already impressed in PRX, already out in PRX Quantum, is, I think, a very powerful approach. Now, this paper plays with another thing. So expectation values, but now in particular, expectation values of gradients. There was a very, very hot paper from the Sanadu people where they were able to show analytical derivatives of quantum circuits, extremely important for quantum machine learning, important for a lot of applications that we thought about. But these derivatives were extremely limited because they were only limited to single qubit rotations. So our group, basically Jacob Kotman and Abhinav Anand, thought about what makes that special, and it had to do with the spectrum of those operators. They had two eigenvalues. So they figured out that to be able to get gradients of these fermionic operators, they had to basically massage the generators in this form and be able to show that you can get an analytical gradient only with 4 measurements rather than order 2 to the n. Okay, which is really, really, really cool because we can show here that we get the gradient for that particular H2 example that we've been showing all over here, basically with those 4 measurements. So this it's a very important development that of course we patented, licensing it to Zappata computing. We think it's a very important development because it allows you to efficiently optimize many body wave functions on quantum computers. Which takes me to another application of quantum computers before I end this talk, as I promised, in about 10 minutes max. And that has to do with, the original discussion I talked to you about, the discussion of designing things. Okay, so we call this quantum computer-aided design. I'll explain what I mean by that. Several papers appear there, and again, I apologize. Many of them are already published or in press. So this one is related to the fact that, as we know, Google's machine, and I'm gonna preempt a question. You can ask it, but I'm gonna preempt it already. It doesn't really matter if there's classical algorithms or not that are very close to what the Google machine can do, because if you add a few more qubits, then you will go back to square one, and you'll be able to sample from this circuit better again, right? So this quantum computational superiority, whatever it's called now, instead of supremacy, has also been achieved by the Chinese team of Jiawei Pan, right? In quantum optics. So this is a plot that we put in our paper here, QCAD, where we are looking at, as a function of years, the number of transmons that people have actually been using. And this is the example of the quantum supremacy chip from Google. And you see some sort of Moore's law, so to speak, or, you know, log linear plot of the number of transmons as a function of time. If you look at what the IBM Summit computer can actually simulate, you can see why there is already this gap for supremacy, which is just some task that you can actually do with a quantum machine. So I asked myself, and I gave this project to Teha Kiao in my lab, and then all of these other collaborators also started pushing on it, especially my grad student Tim Menke and former grad student Hannah Sim, former grad student Nicolas Aguaya, etc. And it was, okay, how can we map the simulation of one of those quantum computers to another quantum computer? And where would you do that? Because if you want to design a quantum computer, say study its circuit properties, study its noise models, you won't be able to simulate modules that are large enough as a physical device. So we found, you know, by simple technical work, that we need 16 levels for every 2-level system that we want to simulate. This is very, very similar, obviously, to the basis functions that we talked about in chemistry. Rather than expanding in angular momentum, we're expanding in this non-linear kind of harmonic oscillator type of basis that the superconductor Hamiltonians like transmons have. So these 16 levels allow us to simulate, say, these 2-level systems accurately to what Will Oliver, which is an experimentalist in this paper, a strong collaborator of ours, thinks is needed, right? And also co-advisor of Tim Menke. So that basically means that there is this 4 times penalty to simulate a quantum computer with a quantum computer. And if you believe this kind of plots, then very, very soon, just look at this time scale, very, very, very soon, somewhere around this year or whatever, whenever these chips are around here, we will be able to simulate a quantum computer better with a quantum computer. And this might be one of the early applications, right, of quantum computers. So besides BQE, which I'm telling you mostly about, I'm very excited right now of algorithms for the simulation of quantum computers, ion trap quantum computers, superconducting quantum computers, maybe Microsoft's famous topological machine as well. Regardless, it doesn't really matter. Simulating quantum hardware with quantum hardware, I believe, is going to be another big application. Okay, and I'm skipping some of the technical work here. But for example, you might want to see the energy level spectrum of the quantum computer. This is an example of the spectrum of this transmon measured the ground and excited states. This is by an algorithm called variational quantum deflation. I used to joke with my group that we needed to introduce all the VQA to Z, but deflation is not our algorithm. But anyway, VQE, VQD, etc. So there's so many algorithms, again, reviewed in our paper, but you want to look at these kind of avoided crossings for quantum operations, the error that is related to these superconductors. If you can get these numbers within 10 megahertz, at least Will Oliver believes is enough. So this is just showing you that we can digitally simulate this simulation that hopefully a quantum computer will do soon of another quantum computer. QCAD is obviously much more general. I apologize, this paper is also already published, but this, I believe, but this is basically a quantum computer doing the simulation of quantum optics. Same idea. If you want to simulate, say now, the quantum optics computer of the Jiawei Pan experiment, you might want to verify that in a circuit model Google quantum computer or IBM quantum computer. So for doing that, you might want to think about how to map the phase shifter, photon sources, beam splitters, dot prisms, and mirrors to simple quantum circuits. And that's what we did, and therefore we can simulate this type of boson sampling type experiments that could be done in quantum optics systems, as the Chinese group actually showed. Jiawei Pan's beautiful experiments. So we can actually show that we can, trottleize the time evolution over these systems. So to actually simulate boson sampling experiments. I'm really trying to be conscious of the time. Let me just show you one slide about what Zappata does. So many people are like, well, Alan, you co-founded Zappata Computing. What exactly does Zappata Computing do, right? So besides, Zappata Computing has like 3 divisions. one division that does what many of the software companies do, works very closely with clients doing algorithms. Of course, we are the internal quantum algorithms developers. We are ranked extremely highly. I believe the number is 4 in the companies that have quantum computing patents for algorithms. But another one of our things that we do, and actually this might be of interest to PNNL, is we have orchestrators for quantum workflows. So you could have backends, including Microsoft's. It doesn't really matter to us, but backends that actually run quantum simulations. And what you want to do is build complicated tasks out of different quantum modules. Maybe you need to run several of these different packages at once, sequentially, in workflows where you need to find exactly what is the version of the code that you employed, make it completely repeatable in the cloud or in your on-premises calculations, and actually visualize it. So that's what Zappata does for its clients. For example, this is a early Orchestra has changed a lot. This is an early version of Orchestra showing, quantum computing simulations on a project for British Petroleum. How will a quantum computer simulating a molecule will look like? And they carried out hundreds and hundreds of thousands of quantum computing calculations using Orchestra. So that's the kind of things that Zappata does, and not many people know. Well, what exactly do we sell? Well, we want to be the execution layer of quantum computers at that level. Not necessarily at the level of simulating a single quantum computer, but at the level of really orchestrating the entire variational algorithm and, of course, gate model algorithm workflows. So this is just at the end, just kind of like a really quick overview of where the quantum algorithm simulations are. This is a paper that we did in collaboration with Google very early on, 2016, now seems like 8 years ago, 5 years ago. What I really like about it is that this is a honest to God, so to speak, BQE with no tricks. This is probably the first BQE that was fully scalable. You can see here the pulse sequences that correspond to the circuit that is idealized here. What I mean by that is, of course, the pulse sequences are not exactly the circuit, they are almost the circuit. And then here are the classical parameters. This is the only thing that comes out of the classical computer, and the measurement operators, which I told you already, huge work in reducing this number of measurements. Huge work in the literature on the optimization, but this is kind of like a canonical VQE carried out in the hydrogen molecule that, again, I described this earlier in this talk, compared to the variation to the phase estimation algorithm. So I really like that because that was 2 qubits out of the 9 qubits of the first machine that the Martinez group and Google were developing at the time. And since then, many papers like this PRX have come out. Here we work together with Rainer Blatt's group and Christian Roos. Cornelius Hempel led this 4-qubit simulation of the lithium hydride molecule, followed by IBM's beautiful, beautiful work on 2017 of the beryllium hydride molecule, 6 qubits out of their 7-qubit device. I love these pictures of orbitals painted on superconductors. That's kind of my dream of 2005, kind of realized here in this beautiful figure of this 2017 Nature paper. So this is kind of like a time lapse, right, of what's happening. IonQ made a lot of noise, right? They're going SPAC. They're going to come out. I guess they're going to de-SPAC now. They did a SPAC already, and now they're going to de-SPAC and go into the market. So valued at $2 billion. Just think about that. So this company did this, 3-qubit experiment or so at the time, but now, of course, with all the extra cash they're going to get from this going public, hopefully they really can go to several qubits. I consider ions very important, and I think Chris Monroe and Jun-Sang Kim are going to do wonderful work there. What is the state of the art today? Many people have criticized this paper. I'm actually a big fan of it because it tells you what you can do, right? So this is the Google quantum machine, the same one that did the supremacy experiment. Notice that they were only able to use a 12-qubit plaquette to simulate a 12-qubit hydrogen chain using the simple but still very accurately simulated Hartree-Fock ansatz. And I think the reason I like this paper is because it tells you honestly where we are in the space, right? I mean, you can only run circuits of this depth, right? You can see here that each one of these thetas is actually this number of gates. So this tells you an idea of the number of gates times the number of qubits that they were able to do. I could imagine they will continue to do larger and larger hydrogen chains if they were able to do it. But that's kind of the state of the art as of last year in terms of where we were in terms of quantum computing simulation. Now, coming out of the closet with Zappata, right? A lot of work has been done, of course, with clients, but some of it has never been shown. But in this particular case, Zappata, together with BP, they published one of the projects that I showed you before, the kind of visualization for, of honestly going to the complete basis set extrapolation of molecules like involved in combustion, something that BP will look at. And now, if you really want to simulate very accurately, and as a DOE would like, probably ethene, for example, right? So this is relevant to the DOE applications. You will go to one of these days and say, oh, this will take 17 days on a quantum computer because here are the number of electrons, right? They say the number of qubits is 13 times the number of electrons, okay? And then this will take, 62 days. Again, I'm zero worried about it because you could also fill a room with 62 quantum computers if you wanted, if you had enough money. So that doesn't mean too much. And the second thing is that they did not use a multi-resolution analysis, VQE. For these molecules, it's possible to run the madness type of simulation. So my lab in parallel was developing MRA-VQE. So this is an example where if you actually look at MRA-VQE rather than these extrapolations, you will also deeply reduce this time, right? So this paper, as it came out, was already obsolete. And in some sense, we're trying to work with Zappata and my research group to try to update it, but it gives you an idea of kind of the moving target that quantum simulation is. That's why I'm very excited. So I show you the moving target of the hardware as the hardware is increasing, the moving target of the software as the software is becoming better and better. And as we like to do at Zappata, we provide honest estimates. We will never try to hype quantum computers. Our company will never be out there putting strange ads or hype. We just really try to say what it is. So there is this bet that we did with Leonie Mook about when will a quantum computer do quantum chemistry better than a classical one. I still don't know if quantum chemistry will be the best application for quantum computers. I'm not so sure it's going to be the first one. There may be a quantum machine learning application, an optimization application, or another heuristic. You saw the explosion of the number of NISQ algorithms that I told you about. So it's very hard to predict which NISQ algorithm is going to win. But chemistry, which is one of my favorite algorithms still, or now the QCAD, which is another quantum simulation application, I think it's a big contender. And the other cool thing about it is, as the hardware resources are going up and the software resources will come down, maybe my bet with Leonie Mook published in this 2015 paper will actually, I will win. So just to end, here is the roadmap of IBM, believing they do have a true roadmap. And Google's roadmap was also being discussed recently in the press. It looks like there is a chance of having a variational algorithm in the next few years that does something noisy and interesting. Noisy in the terms of actually doing real noise and real impact, not only noisy because quantum gates. And on that note, I'm going to end by showing you a virtually separated picture of my group and opening up for questions. Thank you for your time. I'm going to stop sharing so you guys can see my face, and
okay,
you can go into Q&A.
Well, thank you very much, Ilan. We may be experiencing technical difficulties with the Q&A session, but I think both Jaime and I have a question. So Jaime, since you have audio as well, do you just want to ask your question and then I'll ask mine?
Sure, that works. Thanks. So my question is, you mentioned that you're not worried at all about the time for these computations because you can just fill a lab with 62 quantum computers. Can you discuss a bit what the requirements would be for the links between the quantum computer?
Zero requirements. They will be embarrassingly parallel. If you, I mean, they have to be calibrated with each other. There may be some overhead in calibrating them because each quantum computer may have slightly different error profiles, and you need to understand them. But each quantum computer can be used to evaluate separately different elements of the Hamiltonian. Or you could pick an element of the Hamiltonian and average over many quantum computers. So, the variational eigensolver needs to do so many measurements that you could carry it out embarrassingly parallel by preparing many quantum computers at once.
I see. So it's not, the Hamiltonian doesn't have to be separable, or it does? I guess I'm a little bit.
No, the Hamiltonian doesn't have to be separable, but obviously the wave function has to fit in the number of qubits of the computer. Okay, so if you want to simulate a 100 physical qubit system, each one of those nodes will have to be 100 qubits each. But there's so many measurements, and that's what dominates this algorithm, that if you have 100 of them, then you can carry out 100 measurements in parallel. And
Okay.
that matters. That matters a lot because this algorithm is prepare, measure, prepare, measure, prepare, measure. Okay, so it's like if you had a GPU, like you would like to have a lot of cores doing the same thing, and that's something that people really don't think about too much in quantum computing. It's obvious from the variational first paper of variational algorithms that we wrote, but people get confused by that and they report these timings as if they were bad and they make no sense.
Okay, thank you.
Great. So I also have a question, and it's somewhat ignorant, so apologies in advance. But you published, or you showed a list of algorithms that were amenable to NIST computers. You mentioned obviously quantum chemistry is one application, but I'm curious, what are the acceptance criteria or the metrics by which you evaluate an algorithm is feasible? And in particular, how do you weigh in things like the cost of basically doing data, putting data into the system, things like that? Can you say something about scaling for those and performance?
Yeah, so my take on, say, quantum machine learning, which is where you can think about data, right? And there were a few papers that just appeared in the archive in the last 3 or 4 days, okay, by several groups, including Jens Eisert, but there was also another group, I forget the authors, that discusses some more formal bounds on or suggestions of when quantum machine learning will see really be useful. And they're kind of sobering, at least the abstracts of the papers. I haven't read them carefully, I just downloaded them. But they confirm a hunch I had for a long time, which is that, at least what they claim they have proved, is that for all intents and purposes, for quantum machine learning, you want to generate your quantum data yourself. And what data will it be good? Of course, data that is inherently quantum mechanical, like, for example, generated by a circuit of quantum simulation. So one of our applications, and I have a grad student working on that, is the so-called quantum autoencoder, compressor and decompressor of quantum states. I didn't talk to you about it today, but it compresses quantum states, decompresses them back, not dissimilar to the classical autoencoders of machine learning. And what is interesting about this work is that you can take quantum wave functions that came out of a proper BQE calculation and then compress them, which basically is not possible to generate perhaps with a classical computer, such data. Whereas using a quantum computer to classify phases or things like that, then you run into the issue of the data, right? Representation. What is more and more done, and this is what Zappata computing does, is use the quantum computer as a generative model, right? So the parameters of the quantum circuit are moved around such that you generate a distribution. If that distribution in some sense has some correlations that are better captured by quantum mechanics, then perhaps heuristically this is going to be a better algorithm. So in some sense, quantum machine learning is a wild west at the moment, but more and more is being understood.
That's really interesting. Can I ask a follow-on? So you showed a couple different loss functions in the algorithms, in the applications you presented. So with the autoencoder, it's really just the loss function. Is how well does it reproduce the original wave function going in?
Yeah, it's cool. And what we do in the autoencoder is without slides, but it's basically, say you have 5 qubits of quantum data, and you want to encode them into 3. That's an example. And then decode them back into 5. So obviously this could be asymmetric or things like that. So you have a unitary time evolution operation, a gate sequence, that what it does is trying to create a product state of 3 qubits with 2 qubits in the state 0. Okay, these 3 qubits could mean anything but state 0. What it tries to separate 2 qubits from the 5. Okay, so it's like in some sense an entropy extraction kind of thing, or in some sense, right? Like you're but other way of thinking about it is you're trying to go into a basis, right, where all the information is compressed in the states expanded in this particular set of qubits. It's interesting because it's connected to something called Schumacher's compression theorem that tells you ultimately, what are the limits of this compression? It has to do with the number of different eigenstates of the density matrix of the qubits that you're compressing through this channel. And what is interesting is that effectively, if you do it as a variational algorithm, as we did, you run this fix numerically, and you see that if your wave function so and so fits in, say, 3 out of 5 qubits, you can have a very shallow variational encoder and decoder and compress 100% of the information, leaving these 2 qubits basically in the 0 state.
Wow, that's very interesting.
So that's very interesting, because now you can go into that so-called quantum latent space, swim around it, and then what we're doing with my student is exploring the quantum phase transition, so to speak, in that latent space rather than in the uncompressed state.
Yeah, I'm interested in what happens to errors as you do that as well, but we have a question, so I need to not hog the time and ask the question that somebody posted in the chat. So the question is, there appears to be a bias in applications for solving the stationary Schrödinger equation. What about time-dependent response or a dynamic Schrödinger equation?
Okay, well, so I'm just getting some text that you're probably listening about, some basically silencing my phone. There's no bias at all. As a matter of fact, I don't know who asked this question, but probably that person doesn't know. When I started at Harvard, my first project that I gave to my second student, Ivan Casal, resulted in a 2008 paper, okay, in PNAS for quantum dynamics. Okay, I'm gonna actually paste it in the chat. I know people cannot see the chat, right? So, but anyway, it was called Polynomial Time Quantum Algorithm for the Simulation of Quantum Dynamics, Chemical Dynamics, cited 278 times. So even since then, we've been working in quantum dynamics. My group has several papers in quantum dynamics. There was a recent paper by Ivan again on quantum. He came back to the problem several years later for vibrational dynamics, a beautiful paper that came out of Australia from him. Nicolas Aguaya, also from Intel, also former student of mine, has also a lot of work in dynamics. PNNL's own Nathan Weeb has worked on it. Now we have him at U of T, but he has worked on quantum dynamics. So I don't think there is a bias. I think maybe my bias is just presenting to you the stationary one, because I have only 1 hour to talk to you about it. Well, feel free to look at the reviews that we wrote in 2019 and 2020 for more work on quantum dynamics.
Okay. Well, we're just about out of time. So I'd like to thank you again for a really nice presentation, nice overview of the field, and thank you very much for your talk. So with that, we will end the seminar. Thanks again to Alon for the presentation and to all of our attendees. Have a good evening.
Take care.